Hello everyone. Welcome to our talk, RSocket Messaging with Spring. My name is Rawson, and here with me today we have Brian and Rob. The three of us worked on the RSocket support that we're going to present, and that's why we're here today. I am a committer on the Spring Framework team. I handle a lot of the web-related pieces, so Spring MVC, Spring WebFlux, web messaging. Brian?
Hi, I'm Brian. I'm working on Spring Framework and Spring Boot, especially on the web parts. And I've been also working with Ross and Rob on RSocket support in Spring.
Hi, my name is Rob Winch. I'm the project lead for Spring Security, and I've been mostly focused on, as you guessed, the security aspects of RSocket.
Cool. All right. Well, thanks. So what we have for the agenda today is I'm going to start off by introducing the RSocket protocol. I'm not going to assume any prior knowledge. So this is probably the key goal for me, is to make sure that you have a mental image about the protocol so you can understand the rest. I am going to show a little bit about the programming model, but I'm not going to get too much into it because right after me, Brian is going to present a pretty cool, I think, Spring Flights sample. So that will give you an opportunity to see more of the programming model in action. And he's also going to talk about the Spring Boot integration. And then after that, Rob is going to come on stage and talk about the security integration. And as the joke went around, just like in real life, we'll see if we have time for security. But we agreed that we should have time for security. So just a little bit of historical background here. 2 years ago, after Spring 1 2017, we had just released Spring Framework 5, and we were very excited about this protocol called RSocket. And the reason we were excited about it is because it enabled new opportunities for communicating, remote communication, and Reactive Streams was involved in doing that. And as a result of that, we thought of it as very much a continuation of the work we had been doing with WebFlux and reactive programming. I do want to ask actually a few questions just to find out a little bit about the audience here. Could you please raise your hand if you have used the web client or any comparable reactive library? Okay, quite a few hands. That's great to see. What about just familiarity? So those who raise their hands, you can keep them down. Raise your hand if you know what Reactive Streams is and you are familiar with the concepts. Okay, very good. So I think we're pretty much on the same page. So with Reactive Streams, basically we have this RSocket, we have this communication protocol, which is similar to other RPC mechanisms. But what was exciting to us about RSocket is that it was a little bit different in that the way it did things. So one of them was definitely Reactive Streams. As I mentioned, we had been working on Reactive Streams within the JVM to make sure that components can interact and not overwhelm each other. But here we have the ability to actually do that across the network. So that was kind of very interesting and very unique. Also, Reactive Streams, RSocket had implementations in multiple languages, but it didn't require code generation. So that was another thing that made RSocket stand out and made it quite interesting to us. You can have the code generation on top if you want, but that's an optional layer. RSocket just focuses on the important bits. And from those implementations, the Java one is actually based on Project Reactor, and that was great for us because we were already choosing Project Reactor. We had chosen it for Spring Framework and Spring WebFlux, so that made it very attractive to us. RSocket wasn't tied to a particular protocol like HTTP2 or the web, so it's pluggable transport layer. And last but not least, RSocket was already in use by some very large companies, and it was designed by some people with a lot of knowledge in how to write network protocols. And as you will find out when you take a look at rsocket.io, the protocol is very well laid out and very easy to read, which again makes it stand out. That's not always the case. how well things are spelled out. So fast forward 1 year, RSocket is now in the Reactive Foundation, which is a Linux foundation, and you can see that there is broader participation even. That's where we expect the Reactive Streams itself is going to be as well. And fast forward 1 more year to today, we have support in all of these, either already we have support or we have upcoming support in all of these Spring projects. And the ones we're going to talk about today are Spring Framework, Spring Security, and Spring Boot. Okay, so I'm going to get into the RSocket protocol, but before we begin, just one little preface or disclaimer. So you will see a lot of comparisons between RSocket and HTTP, and I think that's a natural way to think about it, and I'm personally going to also make comparisons with HTTP today because that's a good way to learn about something new. But I want to caution against taking that comparison too far. While it's true that RSocket enables some new things where HTTP, that you cannot do with HTTP, at the same time, I don't think of RSocket as a strict superset of HTTP. In other words, it's not something that you will just go and replace HTTP everywhere and just get more. So there's two sides to that. First of all, it's not everywhere a replacement. And number two, it doesn't necessarily match all the features of HTTP either. HTTP is really good for communication on the web between very loosely coupled, very different agents that talk to each other. There's a lot of nuanced features about content negotiation, about caching with proxies in between. That's really what it's made for. Whereas within the firewall, I think that's where RSocket shines because it gives you new opportunities for how to do things if you're doing microservices and you need to communicate between remote nodes. I don't want to pigeonhole it, right? You can still use RSocket over the web, but I just want to give you this little thing to think about, that as we compare to HTTP, don't think of it as a replacement. Really, they each have their own strengths. So what is RSocket with that in mind? So I'm going to start with a kind of a relatively simple definition that it is an application protocol for multiplex and duplex communication. Does that sound familiar? I remember a few years ago when we got so excited about WebSockets, and those are exactly the things we were talking about, duplex, multiplex communication. The thing about WebSocket, however, is that it's very, very low level. It's pretty much TCP with framing, and you need a messaging protocol on top to start to do meaningful things. You need some infrastructure. And that's where RSocket actually is a lot more than that. It's an application level protocol. It provides a lot of features. It runs on top of WebSocket, but it isn't tied to WebSocket. So I can use RSocket over the web with WebSocket, or if I'm inside the firewall, I can use it with TCP. So it's not married to any one particular transport. So what are the features? So we're going to go through those features and learn about the protocol in this way. What can we do on top of WebSocket with RSocket? So first of all, RSocket is a multiplex, provides a multiplex communication with 4 interaction models. And what this means is that we're going to have a single physical connection, and then we're going to be doing a lot of requests on that, sort of like HTTP2. And what these interaction models, the first one is going to be easily compared to HTTP because it is a request and response. And you can see here, those are the actual names of the frames that are in the protocol. The request response frame is actually very similar to the payload frame, but it has a different name because it tells you what kind of interaction you're going to be performing. That's because we have other interactions. So for example, the next one here is a request stream. So this one, you have one message, like in HTTP, the request body going to the other side. And then the other side is responding with a bunch of distinct messages. So this one in HTTP, you might compare to server-sent events, except it's not one stream. It's already broken down into distinct messages, and they're presented in that way to the application. So that's built into the protocol. In addition, as we will see, there is back pressure which is layered into this. So not only is this broken down into messages, but it actually works well with back pressure, so we can tell the server to slow down or stop publishing these payloads. And as we will also see, this can be done from both ends. So, there's similar to SSE, but also quite different. The next interaction is a request channel. This is where both sides are going to be sending streams of messages. And you can see again that the first one tells you the name of the interaction, the request channel frame. And then after that, both sides are basically continuing to send payloads. Now, I want to put a reminder that we're talking about a multiplex connection. So don't think of this channel interaction as a way to kind of do many things. You can still do request response, you can still do request stream. It's a multiplex connection already. So use this only if you actually have a scenario where both sides need to stream to each other. And then there's also a fire and forget. So this one is without a response. You don't know whether it was handled, when it was handled. This is just a fast way to send something to the server, and that may be okay in some cases. So all of these 4 interaction models, you can actually do them from both ends. So this is where we start to also see new things that we cannot do otherwise. That's a duplex communication. So typically, what you will have is a client connecting to a server, and then making a request, any one of these kinds of requests, and then the server is responding to that. But the neat thing is that actually, once you have the connection, the server can do the exact same things. So the server can initiate a request, any of those 4 interaction models, and then the client is responding. So that's basically the reason why in the RSocket protocol, there is the notion of client and server, because initially the client connects to the server to make the connection. But once you have the connection, the protocol calls them requester and responder, because they're completely symmetrical. Either side can be a requester, and then the other side can be a responder. So that enables some interesting possibilities, which we're going to see, I think, one of those in the sample that's coming up. Okay, so the kind of like the main feature of RSocket here, support for reactive streams. So what this means is that whenever you have a streaming interaction, so that would be a request stream or a request channel, if one side is streaming a bunch of payloads to the other side, we don't want the consumer of these payloads to be overloaded. So that's where the initial frame, in this case the request stream, is going to indicate how many payloads should be sent. And after those 2 payloads, the responder has to respect and wait for more demand. It cannot produce any more payloads. And a little bit later, or a lot later, the requester can submit another request frame, request N frame, and that indicates more frames to be sent. So you can see here the back pressure in action. In fact, this is the same Reactive Streams protocol which governs how Reactor, Project Reactor, and others work, except these semantics in this case are implemented and built into the protocol. So the signals that normally flow between the components, in this case, are flowing between one side and the other as request frames. So cancel, on error, all of these things are built into it. All right, so let's take a quick look at this. I haven't shown any of the Spring and Java implementation yet, so I'm not going to focus on what the client side does. But I will mention that there is a CLI for RSocket, so you can run these commands from the command line. What I'm going to do in this case is I'm going to run a server. So you can see that with a -- server. And the -I means input. So the server is going to, whenever somebody connects to make a request, is going to be responding with the data that I'm giving it. In this case, I'm pointing to dictionary words. And we're going to do -- debug. We're going to do this on a TCP localhost port. So the server should be up and running now. And now what I have on this side is, I'll come back to the details of it, but basically we're going to connect I'm going to look at the frames of what's happening. Okay. All right, so we connected to the server, and you can see there's an initial setup frame, which actually helps to communicate some settings, parameters for the connection. And I did not specify any demand from the client side, so the server is not sending anything. These are just keep alive messages that you can see here. So now I'm going to express demand of 5. And over here you can see in the beginning that we got a request stream, and then that included 5. And so we got 5 dictionary words back, and you can see those here as well. Now I'm going to ask for one more. And you can see the request end frame. So the client sends the server request end frame, says, give me one more, and the server responds with one more. Or I can say, give me 50, and I get 50 back. So this is just a very simple demo to show you back pressure in action and the frames that are going from one side to the other. Because we'll be using Reactor, just like in an actual reactive application, normally we don't typically deal with back pressure directly and explicitly. The same thing is going to be true here. We're just going to keep writing and expressing our logic with flux and mono, and the back pressure signals are going to be transparently flowing between requester and responder. Another cool feature is session resumption. So if I have one of these things streaming, right, if I have connectivity lost, then I've produced and pushed a couple of items, but that's all I've been able to do. Well, there's a cool feature where the client tries to reconnect, and when it reconnects, instead of starting all over, it sends a resume frame, and the client and server understand where you left off, and then they continue sending. So the cool thing about this is that it's completely transparent, and the server, from a programming model perspective, you don't have to do anything for this to be supported. Just the connection can drop off, and the client can reconnect, and it just resumes. And the other thing which is nice about this is that because of the back pressure, it means that there isn't a lot of caching required to make this happen. So eventually the back pressure will make it stop producing, and you only need a little bit of cache in order to wait until the session resumes, and then you can continue from where you left off. Now the back pressure is for individual streams. What about the total number of streams or the total number of requests that we can have on a connection? Well, that's a feature called leasing, and that allows the responder to send to the requester a lease for a certain number of requests that can be made, and that allows the requester to make as many requests. So that's like request throttling, basically, and it can be applied from both sides. Also, there are features like fragmentation reassembly, as well as heartbeats. These are kind of low-level fundamental features that are necessary for this kind of connection-oriented protocols that are supposed to be long-lived. Okay, so what's in the messages? Here you have all the request interactions at a glance. Pretty much all of these are quite similar in format. They both contain data and metadata. So what is metadata? Both data and metadata are, we express how they're formatted through MIME types. So for example, there is one RSocket extension that defines a routing metadata, and you can see that there is a MIME type for that. And that tells us where the message is going, which could be a simple mapping for the server side or for the responder side, or in the case of Spring Cloud Gateway, or if there's, maybe it's not from A to B, but there's some routing in the middle, there might be some more things in the routes. Composite metadata, so anytime you want to do more than just a route, if you want to do security and routes and tracing and metrics, other things, then you will need composite metadata, and that basically means that you can have multiple types of metadata in it, each with its own MIME type. So again, if you look at all the request interactions at a glance, the first frame in every request is going to be the most important one in terms of metadata, because that contains routing, security for that interaction. So we're going to say, okay, here's the request response, here is the route for it, so we know how to handle it on the other side, and here's the security information, so we know what the authentication and authorization should be for that. All the other payload frames, they can carry metadata, but we typically don't look in that. That's just something that's not typically required. So how do we know which metadata MIME types we're using or for the data? Well, client and server agree to that in the beginning. There's a setup frame in the beginning which the client sends, and the setup frame contains the conditions for that connection. And the server can agree, or if it doesn't agree, it can close the connection. But basically, it's just a one-way frame that defines the connection. And then after that, each side can begin to send, make requests to the other. Okay, so I'm going to talk a little bit about RSocket Java. The Java implementation for RSocket is very, very minimal in terms of API surface. Its main goal is just to implement the protocol. And as you can see here, we have one main contract that expresses the RSocket interactions. So we have request response, request stream, request channel, fire and forget. If we are going to be sending, then we get this RSocket and we use it for sending. If we're going to be responding, then we have to implement this interface and register it, and that's how the responding works. And of course, if you look at the API, this payload, I mean, that's basically giving you raw data and metadata, so there's a lot of room to make this nicer for application development. But again, that's not really what the Java implementation wants to do. It just wants to provide a minimal foundation. You can also see from the signatures that it's using Reactor, Flux, and Mono, and that's great because we kind of already used to working on that level, and because it gives us a declarative programming model that deals with the back pressure internally. So just quickly to show you an example of how you would start a server. You can see here we do that through the RSocket factory, and then there's this acceptor, and that's the thing which accepts new connections. We're going to return the responding RSocket from that. So that's our implementation of how to respond to interactions. And we're also given the setup, which tells us about the connection, and we're given a requester that we can use to talk back to the other side, to the client. And then from a client side, well, it looks identical actually. But as a client, we can also be a responder. So you can see here that absolutely symmetrical setup is in place. And now you can use the RSocket factory to set up quite a few other things about the connection. You can set up interception. You can set up the heartbeats, intervals. You can set up metadata format. You can specify a lot of things here. But here we're just showing a minimal example. So finally, for the Spring Framework support, thankfully that's fairly minimal as well. So I'm just going to show quickly, and we're going to turn over for the sample. Well, first of all, we have an RSocket requester, and that wraps that RSocket contract that you saw, and it gives you, first of all, a fluent API instead of a template. And it also gives you higher level objects. You can work with higher level objects, and the encoding and decoding is automatically handled. And then for responding, currently we have support for annotated message mapping methods. So if anybody's used Stomp over WebSockets, or you could have used them with JMS, these message mapping annotations could be familiar. Here's an example. This is a controller annotated class, although the controller annotation is something that you can customize, you know, if you want to use your own and call it RSocket responder or anything else, you can do that. So that's an example from the a snippet from the sample. You can see a message mapping method which is responding to requests. Notice that there isn't anything that says request stream that responds to request stream interactions, but you can tell that from the method signature. It's taking one thing and it's returning a flux of many things. So that's sort of implicit, you know, it's not like a rigid contract. And that's an example of using the requester. So here we get the RSocket requester builder injected. That's with Spring Boot, actually, in this case, in the sample. And we're going to use this requester. We're going to connect to a server. And then you can see that we can use it to make requests. Down here, we're getting the requester. And we're making a request with a route, the given route. And then we're passing some data to the other side, and then we're retrieving back airport locations. But I'm going to turn over to Brian now, who's going to show you a pretty cool sample with flight radars and flight tracking.
We're going to see RSocket, but this time in the context of a Spring Boot application and a sample. So first, we need to talk a bit about the use case and the sample. So in this case, we're considering airport radars. So for example, Austin's airport radar. So each radar is collecting data about aircrafts flying around within its range. And let's say it's sending all that data to a particular application, which is our radar collector application. So this is a Spring Boot application that will collect all the data from many, many airports. And it's also got a local database with a list of all the airport radars it knows about, their name, code, geolocation, and so on. So for the purpose of that demo, we're not using real data, of course. We're generating that, and I'll show you that quickly. So once we've got all this, we're able to expose that as endpoints, as services, using RSocket over TCP. And with that, we've got here a few examples of routes that we're exposing. We've got located radars within, so within a particular pair of coordinates, we want to have all the radars that are within that zone. We can then ask about a particular radar, its information, or we can even listen the radar for all the data, all the aircraft that are flying around. Now, the ultimate goal would be to have an application that a browser can connect to, and we'd like to have an interactive map where you could see the radars, the airplanes, and everything real time, plus some contextualized information because you have a user preference, you have a user profile, and you want to have like your personal profile and other things. So that's the demo, and on the flight tracker side of things, we'll have some services, so the usual with having the radars in a particular zone and listening for many radars this time for all the aircraft signals. And we also have new services like fetching your own profile or fetching the profile information for someone else. And this time, because we're using a browser, we're not using the TCP transport, but the WebSocket transport. So that would give us a quite interesting picture, and we're going to check that out. So first, I'm going to start the radar collector application. So as we're going to see, that radar application, so the collector is starting on port 9898 on TCP, and that's a Spring Boot application. And we'll start the tracker application. That app is using Netty as well, and we're starting on port 8080. So now let's take an actual look at the application. So here, by default, we're using Rosson's profile because we don't have really security yet. And we can see that we're seeing radars, we're seeing all the planes flying around. So I can see that a particular plane has a particular name, and same thing for a radar. Of course, when we move the map, we'll get the same information updated. So one interesting thing here is that the first difference with doing that with plain WebSocket is that we actually have back pressure control. So here with that little widget on the bottom left, that's the actual request demand that we're making every second that the JavaScript client is sending to the server. So we're asking for 50 new signals every second, and that's why we see the airplanes being updated. But if I lower that number, then at one point we're getting less and less signals, and it's almost crawling to a stop. And that's because we're asking for less and less data at one point. So we're seeing less updates, and it's almost stopping. So if I even go lower, it should be even stopping. And when you update that again, we should see like big updates and the aircrafts being updated a bit more. So that's the example of back pressure control. Let's see how this works in an actual application. So here, we've got our application running, and I'll show you first the radar collector. So the radar collector is a Spring Boot 2.2 RC1 application, and we currently have like two interesting one particularly interesting starter, that's the new one, the Spring Boot starter RSocket, and we only need that to start an RSocket TCP server. We of course have a few other things like Spring Data, MongoDB Reactive, and so on to get the actual data from our database. The other interesting part is the application properties for radar collector, because we are here using the required application properties to say, I'm going to start an RSocket server on port 9898, and I'm going to use the TCP transport by default. So those are the two required things that you need if you want to start an RSocket application with Spring Boot. Then we can take a look at the airport repository. So just so you know, at application startup, we're just storing a bunch of airport data that we have locally and in our database. And we have that repository available in our application, so you can find an airport by its code or by its location. Once we have that, the other missing piece is the location information and all the signals that we're generating. So this is actually the aircraft signal. So that's the raw data that we're sending. So this is the call sign of an aircraft, its location, bearing, and so on, and the capture time. So at a particular instance, if you want to look at the broader picture, it's the actual aircraft trace, and that's where we are doing the probably naive things about calculating GPS coordinates and distance and so on, but that's how we're generating the fake data that looks somewhat realistic in our sample. If you're interested, it's all there. So this class allows you to calculate distances and to generate that fake data, but then we need to produce it at some point. And we're using the aircraft trace generator. So that's one of the other big piece of that application. So that generator is a component in our application, and you can ask it, give me the traces for, all the traces for a particular airport. So once you get all those traces, you can get them updated, and you can have signals over time, and that's how we can draw things in the end. But here the other interesting bit is that we are actually storing the traces in a local cache, so that whenever you move the map, you're not seeing a picture that's totally different. We're not generating something that's widely different from what you had. So that's why we're storing the traces locally in a cache, at least temporarily, so that it doesn't look crazy. Now the RSocket specific part is for the radar collector is our controller. So like Rossen showed, it really looks like a regular controller, but this time for message mapping. So we're getting our repository in our generator, and from there we can expose several services. So we can find a radar by its code using our repository, and we can turn it into an airport location and send that back. The other interesting one would be the message mapping. So when you want to listen to a particular radar, you can send a message with the actual radar code in the route, And Spring will map that code to the variable, destination variable here in your controller handler. And from there, we can find the radar in our repository to get all the information. And from that radar, we'll generate the traces for that radar, and we'll stream that information to the client. So how does it look from a test perspective? So if you look at the radar collector test, so this is a Spring Boot test class. So this is pretty much a real integration test with actual servers running. So here we are actually telling Spring Boot to create the server not on a fixed port, but on a random port instead of 9898. And so because it'll be random, we need that information later in the game. So that's why we have the local RSocket server port annotation. So Spring Boot can give you that information back once the server is started. And we are also asking Spring Boot to give us a requester builder. So what Spring Boot will do is not just creating builder for you, it will auto-configure a lot of things for you. It will auto-configure the codecs and all the preferences that you've expressed in your Spring application. By default, with the RSocket server starter, we are providing 2 codecs that we think are interesting in the RSocket world. The first one is JSON using Jackson, because we think it makes sense, especially from server to browser interactions. But we also know that behind a firewall and over TCP, or whenever you need to be really efficient, you probably want to use something like CBOR. CBOR is a binary codec that you can use, and it's actually a module of Jackson. So it's really, from a pure developer perspective, if you're used to using Jackson, it's just a switch. So here, when we're calling find a radar by code, you can see that we're using the requester builder. We're asking for a particular data mime type. During the setup frame, we're asking for application CBOR. We're connecting over TCP using localhost and the port. And this time we can then use the requester. So when connected, so this returns a mono. So it's only when you subscribe that you're actually trying to actively connect. So here, whenever we're connected, we're getting the actual requester back in the flat map. And so we're asking, give me, for that route, the information for the airport location. And we're getting still a mono. And if you're familiar with the Reactor test constructs, you can use a step verifier from Reactor test. That's a nice way to test a mono or a flux. You can also use blocking, but in that case, I've used step verifier if you want to test. So I'm testing that the next element that I'm being sent is actually that airport. I'm testing the code and the name, and I'm verifying that everything is being completed properly. So if we look at the data here, we're actually seeing the airport location for this. In the case of streaming aircraft signals, so this is not only a request response, but a request stream. We're getting a stream of information back. Here, it looks a lot like the previous one, so still connecting using CBOR and so on, but this time we're retrieving a flux. Because it's potentially an infinite flux, we're asking for just the first 20 elements, and we're collecting all that into a list. And that's how, in this case, the test is checking that the generated signals all use a particular pattern when it comes to the flight number, that it's always a 2 letters and then 3 numbers thing. So here, as we can see, we'll have a list of flight numbers that look all the same, that all match the pattern that we're expecting. So here, we're pretty much done with the aircraft radar so far. So we're exposing that information, and it's being made available using RSocket over TCP. Now we can take a look at the tracker application. So the tracker application will connect to the collector one to get information about the flights. But this application is a bit different from the collector because this time it's not just an RSocket application, it's a real web application. So we're using WebFlux and RSocket because we want to have regular web endpoints, and we also want to serve static resources. And those static resources, the actual JavaScript client is coded in a different module, the flight client module, that I won't show today because my JavaScript skills aren't that great. And but just so you know, this is another probably like popular use case that we're seeing. And in that case, we are merging the RSocket server into the Reactor Nutty WebFlux server, so you don't have like 2 ports or a really complex setup. It's all being done for you. So this time, the properties that we need to declare, it's a bit different. This time we're asking for the WebSocket transport. We're not declaring a particular port because we're using the server port from the web server. But here we only have to say, I'm making the RSocket endpoints available here on that path. And that's where the JavaScript RSocket client will connect to. From that perspective, here in the tracker, we will collect data from the other service, and it really looks like using the requester and streaming that data into our application. So here, same thing. It looks definitely like our test, where we'll fetch data and send an airport location, return a flux of signals, and so on. Now, on the controller side of things, we have something that looks a lot like the radar collector, but the main difference is here, for example, we are collecting all the signals for many radars. So for example, here we're getting a list of radars, and we are streaming many radars and merging everything into a single stream. And we're making sure here that when the client is not requesting enough, that we're dropping data because we don't need really to save it. And also here, the different bit is we don't only have message mapping annotations, we can also have regular web controller handlers in the same controller. So this is a regular controller handler, and in this case what we're doing is whenever someone sends a request here, we're getting the code, and because whenever something connects, a client connects to a streaming service, we're making sure to store the requester that the server can use to talk to the client. So we're storing that on the side, and then at any point you can send a message here, and we'll broadcast to all the connected clients, you should go there. And all the clients will go to a particular location, and we can see how we can do that in a minute.
Can we find out the back pressure demand in the controller, how many clients it's basically asking for, so that we don't have to retrieve that information from the database?
So the question is, can we find out about the back pressure demand? You can, but it's actually transparent for you. If you're using fluxes all along the way from the controller to the database, you don't have to deal with it. It's actually, the demand is being translated along the way. So that's here in our case, that's how it's done as well. So we will try something here. So just to show that we've got, so this is our application, and I'd like to show you just a couple of things before we end. So just to show you that the RSocket CLI still works. So here we'll send a request to our flight tracker application, but we're using, just to show you that we can also use specific metadata formats. So here we will ask for streaming data for 3 particular radars on the WebSocket endpoint, and we will get all that data for all the traces for a few aircrafts and so on. The other thing that we can show is actually sending people to JFK. So all the connected clients will go to JFK instantly, and that's it. So that shows you how a server without any other client interaction can use the requester and be a client of some sort, so a requester, and send requests to a client. So it's really a two-way communication thing. All right, back to this. So we've seen the basics. So this is just a summary, but we've seen all that. What you need to start. So the kind of things you get out of a starter, Spring Boot starter. How to start a TCP server. You just need a starter, and you need a couple of application properties. Same thing when it comes to WebSocket server. This time you're using WebFlux in RSocket, and you also need a different set of properties just to create a different type of app. And as well how we can get a requester automatically configured by Spring Boot, and how you can test things. The other important thing is that we are providing more things, more ways to customize your RSocket experience in Spring Boot, and that can be pretty useful for extending and adding support for more things. So in that case, we can use a factory processor. So just before connecting, you can be there and tweak the connection phase or do something with what's happening with the actual RSocket connection and the protocol itself. What future work? We will probably do things like improve testing support in Spring Boot. So instead of starting an actual server, we could use a local inside the JVM server. We could have actuator support and so on, many ideas, but we're just getting started. I'll let Rob explain about security right now.
All right, we did deliver on our promise of if time for security, we will cover it. So there we go. All right, so we do have a lot to talk about in terms of security, but before we go into any of the details about how we cover security, how to do it in Spring Security, I want to kind of give a picture of how it fits into our application. So here you can see the flight tracker is going to connect to the radar collector. And as Rawson was mentioning earlier, there's metadata that can be included in the first frame, and including the setup frame. So here we're doing basic authentication. It's not to be confused with HTTP basic, because it's a different protocol, so you encode things differently. But basically you include the username and password in that connection. And then once you've set up that connection, then Spring Security kind of decorates it. And we saw earlier in Brian's slides how there's basically a processor. Spring Security hooks into that processor to wrap the connection. And it associates the user that you just established in that connection throughout that entire connection. So you pass the credentials one time, and then from then on, you can use it to make authorization decisions. So here you can see this is kind of like the little pipeline that Spring Security would build. And there's like an authentication at connection that's optionally available, depending if you chose to do that or needed to do that. And then there's also a possibility of doing authentication per request. And then finally, you do your authorization decisions. And then after all that passes through, the actual existing application code will execute. Now, there's different times where you might want to do different things. Authentication at connection makes sense when you're doing a single client connecting to a server and using that connection just for one user. So that, for example, our JavaScript application will connect to the flight tracker application, and it's only going to be one user, so we don't need to send on a per request basis. And in fact, for our radar collector application, just for simplicity, and because of our authorization rules, it's just a super user that's connecting. But let's say that radar collector needed to do something like rate limiting, or there was some authorization specific to the users. Then at that point in time, you would need to either send just authentication at request time, or you could do both. So you could authenticate at connection time, do some sort of specific authorization logic based upon the super user to see if the connection is allowed. And then for each of the individual exchanges, you could do use authentication at request time and then do special authorization logic on each request. Does that make sense? All right. So this is kind of how the flight tracker application will work. We'll have the JavaScript application will get a JWT from an authorization server. And then after that, it's going to set it in the setup frame, very much like our basic authentication, but it's going to do it using bearer authentication metadata. And at that point, it will set up, the flight tracker will exchange a public key, get the public key to validate it. It'll validate it, the JWT. And then, again, at connection time, it will associate that JWT with the connection, and it can be used for authorizations going forward. And here's just kind of the big picture of what everything's going to be doing on the security side. We have the JavaScript application, and it's connecting to Flight Tracker, which is using JWTs on a per-user basis. But again, it's a connection per user. And then the Flight Tracker is doing a single connection to Radar Collector using a super user for authentication and authorization. Okay, so we've covered kind of the big picture. Let's see how we can do this with Spring Security. I guess we're already in presentation mode. Okay, so the very first step, as you might imagine, to adding Spring Security will be to update our build file here. And we need to do it here. And we just need to add the Spring Boot Starter security and RSocket support. And then at that point, I'm going to just go ahead and run the same tests that we saw earlier in Brian's presentation, the Radar Collector application tests. And you're going to see that it's going to fail because access is denied. That's all we really need to do to get security up and running. And this is kind of what you would expect from Spring Security. The same thing happens in a WebFlux application. It also happens in an RSocket application. Now, to fix our tests, we're going to want to be able to know what our password is. By default, it's going to generate a secure random password, but that's not very practical for our testing purposes or for real-life usage. So we're going to go ahead and open up our application properties for the Radar Collector, and then we can type in a username password. Now, one way you could do it is just type in the password like that, and everyone knows plain text is perfect for passwords, right? Yeah. Hey, everyone's awake. That's great. If you're not aware of it, Spring Boot has a command line utility, and you can actually encode passwords using it. So here you can see I'm basically just running that command line, and it's outputting a bcrypt encoded password. So if someone gets a hold of that, they're not going to know what the password is. So we'll just go ahead and use that instead. And now we have, our password is still password, but now if someone sees this properties file, they're not going to have any idea what the actual password is. And obviously, this is still just a demo, but you could do the same thing in your database as well. Now, let's see how we can fix our tests to use a password in them. We have our flight tracker radar. Okay. So now in here, we saw that these tests were failing. We're going to have to add our credentials to the request. And I'm not going to go over the details here, but this is integrating with the RSocket requester that Rawson spoke about earlier. Basically, we have a username password metadata, and that's just the username and password. And then we have an encoder, and the encoder knows how to encode the username password properly for us to read. And then we modify the builder to leverage both of those. Now to take advantage of that, now all we have to do is just say apply credentials. And now if I rerun these same tests, we'll expect that the find radar by code is going to pass, and then the other two are going to fail because we only added it to the one test. Okay, makes sense? Now, as you might expect, if the test actually fails, then so will our flight tracker application if it tries to connect to our radar application. So we need to fix that, and the first step to doing that is we need to, again, update our dependencies. So we'll go into our flight tracker application, and we'll go ahead and add the same dependencies that we had earlier. And once we've done that, then we can go ahead and go into our radar service. And our radar service has much the same setup that we saw earlier in our tests. So we're going to leverage the same piece of code there to get our credentials. And then we're just going to say apply credentials. So now this is setting up that super user that we were talking about earlier. And now if we actually ran our application, this piece of functionality would actually function. But what's not apparent here is that there's also security being added to our WebFlux application, because there's WebFlux, so you would require a username and password there. And then also to the WebSocket connection from the JavaScript app to the RSocket base code. So there's a bit of extra there. Now, it's important to note that we don't actually need the authorization logic for our WebFlux portion of the application, because basically because there is no authorization necessary for these static resources. They're just static HTML pages in JavaScript making requests over the WebSocket connection. And so the only thing we really care about is the only thing we really care about in terms of authorization is at the WebSocket layer. So we're just going to disable authorization here. And you'll see I'm using the new DSL and Lambda support within Spring Security's configuration. We'll cover more of that in Hello Spring Security 5.2 if you want to take a look at that. But we'll kind of gloss over that for now. And the last piece that we need to do in order to get this to function is make it so that we can actually authenticate our user from the JavaScript application to the flight tracker application. And in order to do that, we could use a username and password as we did earlier, but it'll be a lot more interesting, as we mentioned, using a JWT. So let's see how we can do that. We'll go ahead and open up our build Gradle again. And we'll add a couple of OAuth dependencies. The OAuth 2 client is just going to be for testing purposes, so it could be a test dependency, but simplicity and moving along, we'll just make it an implementation. The resource server is how we're going to validate the JWT. And to do that, we also need to update our flight tracker application here. And we're going to add resource server. This issuer URI is just how we find the public key that we need to validate. And Spring Security will discover it based on that issuer URI. And the client-based properties are, again, how we're going to do our testing for that chunk of code. Now that we've done that, we need to update our test as well. So we're going to go to the flight tracker application tests. And we're going to go ahead and add some code that allows us to test this easier. And all this is doing, this is pretty much what we were doing earlier with the username password in the other test, but it's a little more advanced because you actually have to get an access token from the server. So we're not going to go over the details of that, I'm going to do some hand waving because we're squeezing in security if we have time. And we'll say that's basically getting an access token, and it's including the request. And then all we need to do now is just say OAuth 2 login for login. All right, so now if we run this test, it should go ahead and pass. And of course it doesn't because it's a demo. Why would it pass? Why would it pass? But let's see here. Here we go. Let's see. Factory method is. Oh, I know exactly what we forgot. So I tried to skip one section because we're running out of time, but that doesn't help matters any. Okay, so what we needed to do is we still need to add to our flight tracker a so RSocket Security out of the box is defaulted, but it doesn't actually use the JWT configuration. So what we need to do is we need to do our RSocket Security config. And all this is doing is it's telling it explicitly that we want to do a JWT-based configuration instead of trying to do basic authentication. And it basically wasn't creating the username password-based authentication because it saw that, but it wasn't toggling this configuration here. So now you can see we get the green check mark as we would expect. All right. From there, we still know that there's some problems with this code in terms of it's not actually functional yet. And the reason for that is if we changed our profile to be like Brian, the test is not going to pass. So we'll just go ahead and demonstrate that real quick. So it's because we're hard coding the login in our controller code to be Rawson. So we need to be able to figure out how we can actually leverage the information in the authentication object to change how the behavior of the application. And so here we're running that test. And you'll see that I ran the wrong test because that was the one that worked beforehand. It still passes. I wanted to prove that that one still passes. You see that I know what I'm doing. And so this one's going to fail as we just discussed. And the reason for that is, again, we've hard-coded that behavior. So let's go ahead. Again, we need to start off by updating our build file here. So in the flight tracker application. And the reason for this is most of the support for Spring Security is actually built into RSocket directly. But the place that we need to integrate is in Spring messaging support. So Spring Security also has a hook in there. And we'll see how that actually happens in just a minute. So we're going to open up our user profile controller. And in here, you can see hard-coded username, right? Only if we have time will we add security. So the authentication principle is basically just the current principle of how we've authenticated. In this case, it happens to be a JWT. And to leverage that, we need to get a login. And the login is getting from a claim. So the JWT has claims, and these are just basically assertions about the currently logged in user. And it happens to be preferred username. And so, whoops. So now if I rerun the same test that we had before, maybe we'll do both of them if I see. Here we go. So now if I rerun the same test, this is actually going to fail because I wanted to show you one other thing that you have to remember to do. And by that I mean I almost forgot to do it. Flight tracker application. So it basically can't resolve that because it doesn't see the argument resolver, which is kind of the hook into Spring's messaging support for it. So that actually has to be configured. And then once you've run your tests, now that you know what not to do, you know that these will both be green. Okay? So now we're actually able to fluctuate the user based upon the currently logged in user. And now if we logged in as Brian or Rawson, we would see their radars that they have configured. Now, the thing is all these tests look like they're working and everything looks like, hey, we're all ready to go and everything's going to work. But the reality is that the JavaScript-based application is using a different metadata type. So we talked about how you can use composite metadata, but the JavaScript application is actually using JSON for its metadata. So we need to actually customize how Spring Security is reading in that metadata to get the access token so that it is read from the JavaScript-based application. And we're going to do it a little bit faster because we're running very short of time. All right, and we'll just go over. We'll go over the code versus. Let's see. So the first thing that we need to do is there's a way to extract data in Spring Security. So you get basically the input is a payload exchange, has the payload that Rossin talked about earlier, but the MIME types as well. And then we just basically extract out using this metadata extractor, which is built into Spring. We extract out basically the bearer token. So there's nothing fancy going on here. And then the other thing that we needed to do was we needed to update our configuration here. And we basically grab that converter, and then we create a custom authentication payload interceptor. And those are those little gray boxes that we talked about in the diagram earlier. And then we make it available as a custom payload interceptor. So no longer are we saying JWT default, we're adding that manually. And by doing that, we now have the ability to extract out the JWT from a different metadata type. And the last piece that we really need to do in order for this to work is update our JavaScript. And since you would lose respect for me as a security professional if I did any JavaScript coding, I stole Brian's JavaScript, and we're going to go ahead and compile it real quick here. Oops. And it's compiled. And now I'm going to go ahead and start up these two different applications. So we have the radar collector application. And then we will start up the flight tracker application. So now I just get kicked to Keycloak, which is our authorization server, because it tried to get an access token. I'm not already authenticated, so it wants authentication. So I'll just go ahead and log in as Brian. And you can see it brings up Brian's profile, and it also brings up his preferred airport. And then we'll do another one here, and this time we'll log in as Rossin. And this, again, is just using that custom code where we resolved the current JWT and figured out which user to use. And then here it's going to be doing Cambridge. All right? Let's see. So now we're going to skip back to the slides very quickly. And we've demoed that. I want to mention that there's some related talks if you get time, but mostly just go ahead and go on there and look at the reactive tag on the schedule. And this is our source code for the Spring Flights application. We tried to make it so that if you look at the commit history, it'll give you kind of a story of what we told here. And there's a security branch. Don't forget to check that out, of course, at the last minute. But there actually are additional steps for improving security. It talks about how to optimize how to get your principal and how to make it so you aren't dependent on Spring Security, and doing things like method security and custom authorization. Those are all in the commits, and it's fairly well explained in the commit logs. And that's all we have for today, other than some questions. And so if you have any questions, feel free to go ahead and ask.